Hi, my name is David Jensen, and today I'm going to be talking about the LabVIEW Homework 2 for electronic instrumentation. The primary goal of this assignment was to create a calculator of sorts that would take three inputs, function inputs, and evaluate their mean and RMS values and display waveform plots as they move across time. We accomplished this using uh, several sub VIs and an assortment of different blocks and logical flows. So starting out, we're going to talk about the sub VI, which is shown here. On the left, we have the block diagram for the sub VI, and on the right, we have the front panel. On the left here, we used a case structure that will alternate the case between the mean and the RMS logic. And we fed that with three numerical controls as inputs and a numerical indicator as an output. The case itself is determined by this enumerator input, and when the enumerator value changes, it will signal the case structure to execute one of the different cases. So in this zero or default case, this is running our mean calculation, which is shown here. We have each of the three inputs. They're being summed together using these adding blocks and then divided by three, or the total number of inputs, and then sent to our output. The other case is our RMS, which is it takes each of the inputs and squares them first before summing them, dividing them by three, and then taking the square root of that entire expression and then sending that to our output. So as a quick test, we can come over here and we can just use inputs of 1, 2, and 3 and run our mean case, which should give us an output of about 2, as we expected. And then if we switch this enum block to 1, it'll run our RMS case, and we should get something a little higher than that, 2.16. So that is about what we should expect, and we can verify these results with a calculator. But that signifies our sub VI is working properly. So each time the sub VI is called in the main block diagram, this is the code and the logic that will be executed. Going back to the main VI, here is our block diagram. It has each of our calculations and evaluations segmented off. It's nice and clean and easy to see. And then we have our front panel here that contains each of the plots, along with numerical displays showing the values, and a time block, which counts up as each iteration occurs, and then a stop button where we can terminate the execution of the program. So quickly walking through the block diagram, here in the top left, actually we'll start down here with our timer since our functions are dependent on this. So our timer takes the iteration counter and multiplies it with a time step constant, which here we just chose 0.1, but this can be anything you want for either higher or lower resolution. It multiplies this time step by the iteration, which counts up with each iteration. That time is then sent to an indicator and shown on the front panel, as well as supplied as an input to our M1 calculation, as well as our M2 calculation. For M1, we are looking at the sine of pi over 4 times t. And so we accomplish this by taking pi, dividing it by 4, multiplying that by t, and then taking the sine of that. That's fed to a waveform chart as well as to a couple different places. One feeds into our M3, one feeds into one of our sub VIs, and the other feeds into the other sub VI. The reason for this M1 feeding into M3 is M3 is simply a product of M1 and M2. So we just went ahead and fed it in here and simplified our code. M2 is very similar to M1, except this time it is cosine of pi over 11 times t. So again, divide pi by 11, multiply by t, take the cosine, provide that to a waveform chart, and then send that signal to our sub-VIs as well as the M3 calculation. So for M3, as stated, M3 is simply the product of M2 and M1. Multiply those together, provide it to a waveform chart, and then provide that as an input to each of our sub-VIs. Coming out of each sub-VI, we have a numerical indicator as well as a waveform chart. So this will show an updating value as well as a plot for our mean and RMS evaluation as each iteration occurs. The case is determined by this enumerator block that's connected to it. And so in this configuration, this upper one is evaluating the mean case, while this lower one is evaluating the RMS. But this can be changed here. Down at the bottom right, we have a stop button that controls the termination of the program execution, and that's shown on the front panel as well. So moving over to the front panel, we have our top three plots are our inputs, M1, M2, M3. And then on the bottom, we have our mean plot, our RMS plot, as well as a numerical indicator for each. We have a time block that will update with each iteration. And then we have a stop button that will allow us to stop it. So really quickly, I'm going to clear each of these charts so we can run from the start, and we'll do a little bit of testing. Okay, so when we start running, each of these plots will start to update and show the waveform. Each of the numerical indicators will update as the iterations go, and our time will count upwards. And there we go. One thing to note here is that the ranges, the Y scaling for each of the inputs is from -1 to 1, while the mean is -0.5 to 1, and the time, the RMS is from 0 to 1. Looking here, our waveforms are pretty much what we would expect. We have very sinusoidal waveforms for M1 and M2, and the product, M3, the product of M1 and M2, has a shape that is to be expected from the multiplication of two sine waves. The mean value shown here and the RMS values, again, are pretty much what we would expect from this calculation. We can stop the execution using our stop button, and that should pretty much cover it. Thank you for watching.